Now we'll turn our attention to the Birch Reduction, which is another dissolving metal reduction. And just as a reminder, let's talk about reducing benzene, which is this Birch reduction operates on aromatic compounds. And so let's look at reducing aromatic compounds without doing a dissolving metal reduction, just so that we can see the differences that exist. So it is possible to use a catalytic hydrogenation to reduce benzene or other aromatic compounds like this. It just takes quite a bit of heat, 135 degrees C, and it takes quite a bit of pressure, 160 bar. And at that point, we will perform a reduction and make cyclohexane. And under these harsh conditions, one, illustrates how difficult it can be to reduce an aromatic compound. And two, when we have harsh conditions, it's difficult to stop part way through a reduction, right? This is fully reduced now. We've added all of the hydrogen that we can. In contrast, a Birch reduction operates under very mild conditions. And in fact, a lot of these reactions are capable of doing this without affecting other functional groups. So if we have some lithium here, and we'll need a proton source, so really it's just any alcohol, and we'll just use T-butyl alcohol because of the steric hindrance and lack of other reactivity that it has. And we'll need some ammonia as part of our dissolving metal part, and some THF. And of course, this is liquid ammonia, so it will need to be conducted at a low temperature. And an interesting compound happens out of this. We get a 1,4-diene. Well, we should probably look at the mechanism of this and explore this a little further. So let's draw that. So again, we'll have an electron that's been dissolved, and that is going to come in and attack that one of the carbons. And one of these double bonds here is going to break and split off, placing an electron pair on that carbon, the top one. We have to name it something. And a radical ortho to it. So we have a negative charge there. Now we'll bring in our proton source, which is our alcohol. And I'm just going to use a generic alcohol in the mechanism here. So we've supplied our proton. And we still have a radical, which is going to attract another electron. Now at this point, we'll have a structure that will experience several resonance forms. And And so we're going to need to draw those in order to move the double bonds into the position that we see here. So what will happen is those electrons will transition into that bond, and then the electron pair will move from being in between here and focused on that para carbon. That's really resonance, so. Now, considering that we really only get the 1,4 substitution, there must be something special about this resonance structure. And indeed, there is one more resonance structure, but it's just the mirror of this one. But I'll draw it here for completeness. This particular resonance structure is the most stable. And the reason it's the most stable is it has these sp2 carbons flanking it. And sp2 carbons have a little bit more electronegativity, and so they're able to help stabilize this negative charge that exists on that carbon next to it. Up here, we don't have quite the same effect. So, and similar here. So that is why this is the dominant resonance form. At this point, we bring in another molecule of alcohol to form the product. I should also note that we make deprotonated, the alkoxide here. I kind of missed that. So those are our products. Now, we did this without any substitution on the ring. So let's talk about what happens when we have substitution on these rings, because now in our product, these carbons are no longer equivalent, right? This is an sp2, that's an sp3 carbon now. And so the positioning would start to matter. If we have an aromatic ring and somewhere on here is an electron donating group, right? Somewhere on this ring. We do this reaction, then the product that we'll see will have the electron donating group substituted on one of the sp2 carbons. Furthermore, this reaction is going to be slower than the benzene species. The electron donation is going to destabilize the ring when we have negative charges being placed on it. And we're going to want to avoid having a negative charge right next to this electron donating group. That is why we don't get an sp3 carbon right here, because during our process, the sp3 carbons in both cases have a negative charge associated with that particular carbon. And if we have an electron donating group, it is going to want to avoid placing a negative charge right next to something that is feeding electron density into that position. Well, and this is slower, so. Well, if that's the case, what happens if we instead have an electron withdrawing group? Somewhere on the molecule. Well, in this case, the exact opposite will happen. This is going to be much faster. And that's simply because it's going to be capable of stabilizing that negative charge a lot better. And so the reaction will just be easier and faster. And you might already guess where this is going. The electron withdrawing group will be located on one of the carbons that is reduced, or one of the carbons where the electron withdrawing group is located is going to be reduced, simply because that is where a negative charge will be focused. So that one will have a larger negative charge, which will focus the attack there. Now, this is also possible to do on heterocyclic aromatic compounds. And the reaction that we would look at here, and I'm just going to go with some of these 5-membered rings, and so like an oxygen or a nitrogen here, either one, you can do this with. Now, because of this oxygen or nitrogen, and it has lone pairs and it can activate the ring, we will need an electron withdrawing group somewhere here in order for this to proceed forward. It will be difficult, or actually it's not possible without the electron withdrawing group, simply because the ring is activated. And similar conditions, right? We need some kind of alcohol as a proton source, THF as our main solvent. We need the liquid ammonia for the dissolving metal part. And we'll need it to be cold so the ammonia is actually liquid. And the product of this, when you have a 5-membered ring, looks like this, with somewhere electron withdrawing group, right? So it is possible to do on other than benzene compounds.